So hello viewers, welcome to another video on networking. So now we have come on the stage where we have completed all the important topics or all the important topics for the layer 2. And layer 2 is like basically the data link layer. Now we want to move our learning part towards like layer 3. And layer 3 is like networking layer if you follow basically the TCP IP protocol, right? So, but before going for the layer 3, I just want you to revise the layer 2 networking concepts. So, it's a wrap basically, and I highly suggest that you should follow along with this video only if you have some knowledge of layer 2 protocols, like what are the layer 2 protocols, their importance, how they work, and all that stuff. Or else, what you can do is like we have made our full playlist on layer 2 networking protocols. So you just check that out before proceeding with this video. So that is obviously basically you need, because we are going to just overview the important topics protocols that we have already studied. So with that, we just start with the wrap of layer 2 networking protocols. So today, what we'll do, we'll basically revise the long journey. Basically, all the layer 2 protocols that we have seen in our playlist, we'll just revise, and we will see that how all the protocols are actually connected. So let's just start. So these are all the topics that we have seen till so far, right? So basically, what we have studied like VLAN, we have not talked much about the VLAN, but we have studied that, and that is like that works on layer 2. Then we have studied spanning tree protocol, SDP. That there are several videos on that topic also. Then port channels, MLAG, and followed by some FHRP protocols, first hop redundancy protocols. So VAR, VRRP, and VAR. So these two protocols we have seen, and this is like very ordered collections of topics that you might want to follow and study and learn in this particular manner. So first, let's just start with the VLAN. And VLAN basically stands for Virtual Local Area Network. So before we get into the VLAN, there are several things that we might want to look at first. So what is the need? Basically, we want our network to be virtually segmented. That's why we have VLAN in layer 2. And what are the features is like it provides obviously the segmentation, because that's the main intention to have VLAN. Then it provides security, as it you can say it provides segmentation, so we can have extra layer of security. So the person belongs to one segment can't ever talk to the person who doesn't belong to that same segment. So that's why it provides the security, and that's the basic concept of VLAN. If you see, there are only the devices which are in same VLAN can communicate together. So that's the concept of VLAN, and that's how it provides the security. Then it provides flexibility, and it also simplifies the management. What's the types? So there are several types: default, native, and user defined. So the default VLAN is like VLAN 1, obviously. Native VLAN is like the VLAN which, let's say, if there are no device in certain VLAN, then the traffic which is what you can say destined to be go for that VLAN. So that can be what you can say default gateway kind of thing. So it's not a gateway, but it's a default VLAN. So if there are no devices in that VLAN, destination VLAN, so it can be forwarded to that native VLAN. And user-defined VLAN it's like we can create our own VLAN and we can have it according to as per our need, as per user needs. So these are user-defined. How it works is like VLAN basically uses the tagging protocol IEEE 802.1, and it works on that protocol. And basically this protocol defines certain port roles that you can configure, and on the basis of that VLANs work. What are the benefits? Like it provides improved network performance, security, scalability, and also simplified the management. And what else is there for the VLAN for us to look at is like how inter-VLAN routing can be done, how what is trunking, and how Q and Q VLAN mapping is done. So as now we have talked about the port roles. So there are two port roles, access port and trunk ports, right? And we can actually configure VLAN using these commands. So for port roles are like access port and trunk ports as we have seen. So access ports are such ports which allows only certain VLAN tagged packets. Like if there is some port which says like I will allow packets tagged with VLAN 10 only, then it's access port. And trunk ports are like the ports which can allow group of VLANs or it can allow all VLANs basically. So that's the definition of trunk port. So there are two cases. Let's say there is some port which says like I will allow packets tagged with any VLAN number, and there is some port which is allowing group of some VLAN. So that is also a trunk port. And these are all respective configuration commands to configure access port. So for configuring access port, we can go and say switch port mode access and then provided followed by this command which can what you can say configure the VLAN. And if you want to configure a trunk port, then you can just go and say switch port mode trunk. And what helps VLAN, what in terms of what you can say management VLAN provides it, like without VLAN this packet sourcing from MAC-C and destination is MAC is B. So this device wants to talk to this device, but you can see the switches don't have any entries in the MAC, so this packet might get broadcasted to unnecessarily in this finance domain also. Because of that, we have something called VLANs, and we can configure some things in such a way, in some ports in such a way, so that the package is sourcing from C destination is 10, and if we are tagging that VLAN, so it can't unnecessarily broadcast it to this finance domain. So that is the advantage of having VLAN. And these are some of the facts that you might want to know. One VLAN is equal to one broadcast domain. One VLAN is equal to one subnet, and that stands for one broadcast domain is equal to one subnet also. VLAN 1 is default VLAN, we all know. And all ports are configured by default in VLAN 1, that also we know. And there is one fact that only the devices which are in same VLAN can communicate, right? So that might lead you to one question, that can't they talk to ever each other, like VLAN 10 people can talk to VLAN 10, sorry VLAN 20, can it happen? So yes, for that we have something called inter-VLAN routing, right? So there are actually three ways to do inter-VLAN routing. Traditional way with the layer 3 device, and you have trunk link, so all the packets tagged with any VLAN can go through this link, and then it can be routed through this router, and you can basically have static routing, dynamic routing, anything that you want on top of this layer 3 device. Then there is a router on a stick method. So basically in traditional way, right, in this way router can't have so many ports, so it limits the number of switches that can be connected to this router. So to avoid that, we have one switch. So in this switch we can connect lots of multiple switches, because switches are the device which generally have more ports than the router. So then it can be with the concept of sub interface, it can be possible that there is one link with the only one link with the router, and there are sub interfaces on this port that we have configured, and all the packets tagged with any VLAN can go through this and can be routed through this layer 3 device. And then later on, now this is the modern era, so we have layer 3 switches and SVIs. So we can configure SVIs, and there is no need of layer 3 device, because this layer 3 switches are there, and we can have any type of routing that we want, and we can route between VLAN 10 and 20. So that makes our conclusion for the VLAN. Now we'll quickly go through the spanning tree protocol. So STP. So what is the problem? So first, for STP to have in our network, have at layer 2 is like we have layer 2 loops that can even cause broadcast storms and all that stuff, even though we have VLANs, right? So that can be possible. So to avoid that, we have STP, and as per the problem stated, what are the features is like first is like it prevents the loop, right? And there are several features that you can look out. What are the types is like there are several types or several variants of the STPs like rapid STP, multiple STP, per VLAN STP, rapid per VLAN STP, all those. And basically this is some terms like bridge that refers to switch or that refers to device, because bridge is an older terminology or analogy. So you might see somewhere written like BPDUs. So BPDUs stand for Bridge Protocol Datagram Unit, and that are the packet exchange for the STP. So how it works is like it works on concept of port roles and port statuses. So there are certain port roles that usually defined in STP, and there is something called root bridge. So STP selects the root bridge, and then on the basis of that root bridge and how the all the switches are connected to those root bridge, they exchange something called BPDU, and then later on they assign some port roles and port statuses to topology in such a way that it avoids the what you can say layer 2 loops. What are the benefits? So obviously loop prevention, network stability, all that stuff. And actually, what else is like you can set your path for the learning of port channels. So there is one problem that we'll see later. So these are all port roles. Basically, if you just want to see the status of spanning tree, you can just go and say on any layer 3 device, any layer 3 switch, basically show spanning tree. So it will just list you what are the ports and port roles and all that stuff. So there are port roles like root port. So first is root port. So if that, let's say this is the root switch. So for any other switch than the root switch, if the port is directly connected to root bridge or it's like very near to the root bridge, so it will be assigned the port role called root port. So as this is directly connected to root bridge, this is root port. For this, it's the same. Designated ports, like all, there is one say for all the bridges of root bridge, all the ports of the root bridge, they are by default all designated ports. And designated ports are the ports which allows the flow, or you can say transmission and receiving of the packets. Alternate ports are such ports which doesn't process that and allow or transmit or receive the traffic. So that is like alternate port. And backup ports are like if let's say one port's got failed, so backup ports are such port that can be used as backup. STP also detects that and assigns that port. So as of now in this topology we have one layer 3 loop, if you can see. So you can directly understand that having this port as alternate port stops this port or this link to cause layer 2's what you can say loop, because this port will not be used as this is alternate port. So spanning tree port statuses. So basically there are 3 port statuses: learning, forwarding, and discarding. Learning means still the STP is running and haven't the STP is not yet finalized the root bridge and all that stuff. Forwarding, it's like the packet is actively transmitting and receiving the packets. And discarding, that means the port role is alternate and port can't receive or transmit the traffic. So whenever you want to change the root bridge, so you can just fire this command, and this is like for the multiple spanning tree protocol. So we are typing spanning tree, then MST, and this is the ID for MST's what you can say this is the MST0, then you want this bridge to root primary root, so we are typing root primary. This is the command basically, and having fired this command, what it will do is like it will exchange BPDOs from all the ports of this particular switch, and now all the port roles of this switch will be designated port. So what is the problem with the STP is like it provides we want to have port redundancy in our protocol, but STP what you can say doesn't allow us to do that. So how? So basically, let's say we have connected two what you can say ports between these two switches, right? And in order to have port redundancy, so we thought of like this. Let's say if one of these physical ports get failed, so we have this second port in order to have port redundancy. We thought of this and we have connected two ports, but STP will kick in here, and what it will does is like, let's say if this bridge was root bridge, so it will detect that this port, these two connections are causing layer 2 loop, so it will assign port rows in such a way that one of that port will be will not be used because of this alternate port. So that way, that's a problem. But what happens when we scale up? So when we scale up, then this problem becomes and more visible. Is like, let's say in this topology, this is traditional and modern leaf spine topology. So let's say this bridge is a root bridge. So these are the what you can say used ports, and other than that, all of these are causing layer 2 loops. So these all ports will be assigned such role that these ports will be of no use basically because of STP. So you see, we have invested lots of money to purchase physical ports, and we have connected and we have made our topology, but due to STP, we are not able to use these ports. And if you want to learn more in details, so these are all the videos that we have on our YouTube channel. Now that marks our conclusion for the STP. Now let's proceed forward for the port channels. So port channels, that is also known as LSEP, Link Aggregation Control Protocol, that is IEEE standardized protocol. So LSEP, so previously we have seen one problem in STP, like we can't use port redundancy. So LSEP is the solution for that. So it allows us to aggregate the links, physical links, and that way the first feature of that LSEP is like it provides link aggregation, right? And these are all the features for the LSEP. What are the modes? There are basically two modes: static and dynamic. In dynamic, there are again two: active and passive. How it works is like it works on packet exchange called LSEPTUs and dynamic negotiation. What are the benefits? Obviously, the benefit first and far what you can say very main benefit of it is like it provides link aggregation, and it basically tricks the STP. So let's see how it tricks the STP. So previously with STP, we can get port redundancy or higher bandwidth in order to, or you can say because of this situation. So what if we can bundle these two ports in such a way that these two ports should appear as one logical link to these two switches, right? So that no of this actual physical ports gets blocked by the STP, because now these two physical ports are one logical port. So now STP is tricked and it got assigned these port roles. So that way LSEP helps us. So LSEP basically helps us to bundle these physical two ports, and it will make them appear as one logical link to HTTP. And this is the basically the quick configuration to have this kind of behavior. So basically we can use this command to create port channel, and basically for these two ports, let's say these are Ethernet 1, Ethernet 2, we can just go and say channel group something, let's say port channel 10, and then mode active. So mode active is like they actively negotiate, they actively will negotiate for and for the what you can say forming port channel between these two switches, and they will exchange the packet, they will start exchange the packet of like LSEPDUs that you've seen earlier. And having said that, there is also one problem with the what you can say port channels is like whenever they exchange this thing called LSEPDUs, they will put one field in packet which is called switch ID. So this switch ID will be some numerical value. For just demonstration, I have wrote like switch ID. So this switch ID will be some numerical value, unique ID for this switch, and same way for this switch also, it will exchange its own switch ID. And for let's say we are bundling these two physical ports, so for all of the physical links inside this logical binding, for per pair the switch ID packet exchange will be similar. So these ports will receive switch ID of this switch. So for these two ports the switch ID will be same because it is being sent by this switch only. And again, for these two ports on this switch, the switch ID will be same because it is being sent by this bridge. So it will allow us to form port channel because when we create port channel, it checks for all of the physical ports inside that port channel to be receiving the switch ID, the packets with this switch same ID, the same switch ID, right? So all the LSEPDUs should carry same switch ID in one logical group. That's the rule for the port channel. So that makes us to use only these kind of binding where we have two devices, and between these two devices we can group ports. But actually, what if we want our ports to use, we want the port channel to be used as device redundancy. So this is the port redundancy. But what if we want to have device redundancy? So device redundancy means, let's say, what if one of these two devices gets failed? So we can route our traffic through this device or through this device. So we can do this kind of stuff with the port channel because uh, the switch ID exchange pair will be different because if we want to bundle these two ports, so this port will receive switch ID with the colored black. Obviously that's a numerical value, but just for the demonstration I have used this colored analogy. So and this port will receive the LSEPDU with the switch ID colored green. So obviously those pairs are different. So it can't form the port channel over here. So that makes us to not have device redundancy. We can't load balance between devices. Obviously we can load balance between ports. But also we can't use the dual homing of the devices. So these are all the things that we want, but we can't have because of this check from the port channel. So these all are the videos on our YouTube channel. You can go and watch this stuff. And that makes our conclusion for the port channel LSEP. Now let's just talk about MLAG, or you can say VPC for the Cisco, MLAG for Arista. And these both are like vendor specific protocols. So MLAG is Arista proprietary protocol, and VPC, that's the Cisco proprietary protocol. These protocols are most important but they are not standard protocol. But the working of this MLAG in Arista and working of this VPC in Cisco, these both are like very similar. So we'll see what MLAG can do and how it can be helpful. So the problem of port channel, that we can't have the device redundancy, that for that purpose, to solve that problem we have MLAG. So obviously the first feature should be of the MLAG should be it allows the redundancy, and where it can be used. So it is used in data centers, networking, high density environments, and disaster recovery. These are all the use case. And how it works is like it uses the internal communication for the port channel, LSCP2 packet exchange, and some internal working. And what and all our benefits is like we can use port channel to have, you know, port channel forming in such a way that it provides us to have device redundancy. So it basically tricking the port channel. So this was the problem in port channel that we have seen earlier. So now how MLAG can be helpful is like, so these two device, right? If we form a port channel between these two device and we have MLAG over this link communicating through these two switches. So what it will does is like this color analogy is same. This switch is having colored switch ID with green color, and this switch is having switch ID with black color. Obviously, those two are numerical value. Again, I'm saying this, but this is a colored analogy just to explain you and very easily. So if we have MLAG, so what MLAG will do is MLAG will help these two switches to form port channel with this single switch. So how it will do is like MLAG will select one of these switches as primary switch, and whenever they will exchange something called LSCPTUs, they will write switch ID of the primary switch only. So let's say in this particular case, this green switch was the primary switch. So whenever this switch will send LSCPDUs, it will make sure to put switch ID of this switch only. So now the switch ID exchange is will be of this green colored thing, and whenever we want to form a port channel, it will be possible because the switch ID exchange is similar. So that can allow us to form a port channel between these three devices. And this is the sample configuration of the MLAG. And if you want to go in much more detail, so these are all the videos that we have on our channel. You can just go and watch them. And that makes our conclusion for the MLAG. And now we are looking for the VRRP. This is something different than device redundancy and port redundancy. So this is something called gateway redundancy. So gateway is the all you might know entry and exit point of our network. So what if that entry and exit point got failed? So in order to solve that, we must have something called gateway redundancy. So VRRP helps us to uh, provide the gateway redundancy. So that was the problem, and for the solution of this problem, we have a VRRP. And having said that, obviously, the first feature of the VRRP should be gateway redundancy. And what are all the use cases? And obviously, these all are other features of this VRRP that you can look at. And use cases are like it is used in data center networking, enterprise or service provider networks. How it works is like it works on internal communication and packet exchange between devices and something called virtual IPs. And what are the benefits? Obviously, it provides availability, fast failover, scalable, and stuff like that. So we have seen this stuff, port channels, right? Port channels provide port redundancy. MLAG plus port channel provides device redundancy. So what about gateway redundancy? So obviously IP gateway is nothing but an IP address which is entry and exit point of the network. So what if that gets failed? Then we can communicate to outside of a network, and in worst case we can have no internet access. How VRP works is like VRP communication helps us to have something called master and backup IPs. So let's say there is VRP running in between these two switches, and this switch is having some gateway, and currently this is master, and this switch is also having some gateway IP, but this is currently backup, so it won't work for now, and this switch is working. And whenever master gets failed, the backup will be active, and it will take place of that gateway, and it will allow to have all the traffic coming in, and this will be now new entry and exit point of a network. So master will send something called keep alive messages to backup device, and this is just the analogy. You can have multiple backup devices, so this keep alive message will be sent to all those backup devices. And whenever master gets failed, so there will be no keep alive message between the master and backup, obviously because master gets failed. So after some point of time, let's say backup uh, didn't receive something called keep alive messages. So in that case, what backup device will do? Backup device will send something called GARP, gratitude ARP. So this ARP will basically reset the MAC entries for this device. So previously the traffic was going through this device, so there will be obviously MAC address of this device. But now having been sent this GARP, the MAC entries for the gateway IP, it will be now the MAC address of this backup device. So that's how VRRP is working. And now this device will become master. And that makes our conclusion for the VRRP. And what is the problem with the VRRP is like it works on the something called active standby mode, right? So whenever there is one master and one backup, so until and unless the master is not, what you can say, went down, the backup will not be activated. So all the traffics will just have one entry point and one exit point. So this master in that case will be it should be capable of handling the traffic. So in some cases it might cause bottleneck, because there are lots of traffic for those can be those can be causing bottleneck. So how VRRP helps is like it configures virtual IP and virtual MAC on the devices, right? And you can have multiple devices configured with the virtual IP and virtual MAC, and you can have those those devices as gateway configured on the below devices. So you can route your traffic through this device and through this device at the same time. So that way warp can be helpful. And these are all the videos on FHRP and VRRP. So that makes our conclusion for the layer 2. And now we are all set for the layer 3. So that's it basically in this video. And now in upcoming videos we'll see more about layer 3 routing. We'll see all the protocols, right? So hopefully you are all ready and set for the layer 3. This is it for this video. We'll see you in the next video. So until now, you can obviously make sure to learn more things. So we'll meet in the next video. Till then, keep learning and keep exploring.